Wave speed. Alright, we're going to talk briefly about wave speed, otherwise known as wave velocity. So this is the speed that the wave front is actually moving. So if we have velocity, we can remember from last semester that it was change in position over change in time. Translating that to our wave terminology, the change in position is the wavelength, and the amount of time that takes is 1 period, or capital T. We also have this equation where the frequency is equal to the inverse of the period. So if I substitute that into our second equation, I'm left with the velocity, or the wave speed, is equal to the wavelength times the frequency. You can remember it this way if you want to, or this is how it's actually written on the AP equation sheet. Wavelength is equal to the ratio of the wave speed to the frequency. So let's talk about this. All right, so let's think back to our water pendulum in the hallway. If we sped up the paper that was moving, the wavelength would get bigger, right? Because for every drip of water, the paper had moved farther. If we slowed down, the wavelength got smaller, and in some classes, we actually got it so small it became a line for a while. Now, in this particular case, the frequency was set by the pendulum, so it never changed. It was constant. So this isn't always going to be the case. The frequency could change. However, in most cases, when we change mediums or change the wave speed of something, the frequency is going to be what stays the same about the wave. And this will become very important when we get to things like reflections and transmissions and standing waves.